Robotics relies on well-known algorithms, yet developers often have to re-implement them on every new robot, costing countless hours. Existing libraries and frameworks attempt to help, but hardware integration remains a substantial source of overhead in configuration, validation, and iterative testing.
We present Mars, a C-like object-oriented language that addresses this gap by streamlining integration, letting developers get robots moving quickly and focus on more meaningful problems.
To show off a bit of Mars, let's meet Phobos. We built her specifically for this project to show off how Mars supports modularity. She is set up to be hot swappable between different chassis configurations. Mars runs directly on the Raspberry Pi.
Phobos' hardware is abstracted to a configuration file, designated as a .marsc file.
A robot is a tree of components, with the robot at its root, and its subcomponents branching down from there. Each component has a set of subcomponents, parameters, and functions. This chassis is of type skid chassis, which itself extends wheeled chassis in chassis.
This system of inheritance allows users to expect the information a config might include. If our chassis was missing 4 motors, the interpreter would throw an error before any code even executed. However, if our robot used an API that eliminated the need for motor subcomponents, we could simply use the @override command to ignore that check.
If we want to access functionality not natively included in Mars, we can create a Python integration layer in our tools folder. Simply import it into your Mars script and access any function in it. Now, I'm going to show you how easy Mars makes it to switch between Phobos' chassis.
I go into my config, I switch out my chassis, and I hit run. Just one line. And for similar robots like these two, Mars ensures it stays that simple.
That works because both configs are compatible with the code. But what if my robot wasn't?
Meet Deimos, an AWS Deep Racer equipped with an Ackerman steering chassis and a 6-axis IMU.
We connected Deimos over a bridge to ROS2 Foxy. Let's run our demo. If we look at our terminal, we can see that our requirement for tank-style control is not satisfied. Our keyboard demo class expects the chassis to have a drive function that takes left and right velocities, but Deimos takes a twist. Let's swap this for a twist robot class.
Our requirement system is one of Mars' biggest strengths. With this, you know if your code is compatible with your robot before a single line executes. The requirements are expressive, allowing for all sorts of conditionals. Additionally, requirements are checked per the robot the class is instantiated with, allowing for heterogeneous multi-robot support.
With strong documentation and flexibility, Mars is perfectly positioned to expand with the help of contributors.
Imagine a world where you can download an FK script and a config for a Romy, and you know it's going to work before you even hit run. Mars is built around that vision, a world where hardware integration is predictable and virtually effortless. Thank you.